Hello and welcome to this tutorial. Today is going to be slightly different. We're going to look not at a beam or at a bridge, but rather at a column. We're going to apply a uniform compression on the column and then look at the eigenvalue buckling and also at a large displacement analysis of that column when we apply an initial imperfection. So here are the parameters for this model. We have a curved column. It's not a bridge really, it's a column. The curvature is a way to apply the initial imperfection. We are just considering the steel structure, so no concrete, so just direction analysis here. We are doing an eigenvalue buckling analysis and also a large displacement analysis. We have this type of supports, and we're also applying the point loads to apply the uniform compression on the column. We have a radius of curvature of about 3,000 feet. Okay, it's quite wide. I believe this is equivalent to an initial imperfection on the column of about 500. So it's an imperfection of about L to 500, I believe. I'm not quite sure, but I believe this is the initial imperfection here. This is the length of the column. It's 50 feet. We have standard material properties. We have a pin here. Pin is 1 stands for pins and 0 stands for roller. We have a simply supported column. We can click on this button, it doesn't do any harm. Here is the mesh size, 1 foot. Here are the cross-sectional dimensions. Okay, these are the dimensions of the column. We are assigning this profile to that one segment that we have, and we are turning on the whole length of the column, and we're not defining point loads. We could define 4 point loads, but because we have a pin at the first support, we don't need to apply a force there because the displacement is restrained anyway. So we have just one load at 0 foot here at node number 8. So that's this node here, top flange node. The load is equal to 50 kips in the direction number 2. So that's really the y direction or the longitudinal direction. And then at the other end, we have a load of 50 kip on the bottom flange here and top flange here in the other direction. So overall, we have 100 kip which are applied to the column. We are not turning on the self-weight. We're just looking at the effect of the uniform compression. We are running the eigenvalue buckling analysis here. And we are also running a large displacement analysis or geometrically nonlinear analysis. We are tracking 1 degree of freedom at midspan here at 25 feet. Location on the cross section is node number 5, so that's the central node here. And direction 1, so that's really the transverse direction or x direction. And the idea here is we want to capture the out of plane displacements at this node. We are really helping the solver here by specifying a large number of load increments. So the 100 kips will be divided into 200 increments, and that's a way really to help the solver find a state of equilibrium at each of these increments. We are updating the stiffness matrix at each load increment, so that's a modified Newton-Raphson type of algorithm. We are enforcing a minimum of 3 iterations per load increment and also limiting the number of iterations to 100 at each load increment. We can run the analysis, but it takes a few minutes. So instead, let's just look at the results. So we have here the column. You can see how the load is applied. So we have a uniform compression. We can look at the buckled shape, and of course, as you would expect, it is buckling in the minor axis, and you can see here the eigenvalue is equal to 0.46. Okay, now let's look at the large displacement solution. We have 84 load increments, so at the 85th load increment, the solver could not find a state of equilibrium, and you see here how it's deflected. Very large displacement, so we can really consider that this column has already buckled. And as you can see here, okay, load versus displacement curve at the degree of freedom we were tracking, 0.42, so very close to the 0.46 we found with the eigenvalue buckling analysis. Thank you.